Hello grade 12s. Now in this particular video we are still dealing with optimization, so we're still dealing with maximum and minimum word sums, but we're going to look at some past paper examples. So in the first example we're going to look at the IB 2018 question 8. So IB 2018 question 8. You can get all of these papers on the Synsidians website, but I will also upload to the Google Classroom just in case you need these. Now this problem that was asked in 2018, as you can see, had the following. It said, a farmer has a flat sheet of steel measuring 20 meters by 1,2 meters. He wishes to make a water trough by folding the sides up as shown in the diagram below. So this is now a 3D shape, well, a 3D diagram of that water trough. The ends of the trough will be constructed separately and will be at right angles to the sides and the base. So they're just pretty much saying that the end over there and the end of the over there, that will be constructed separately. You don't have to worry about that. The actual sheet, that 20 meter by 1,2 meter sheet, this part right there that got folded up, that's the sheet. Okay, and they also give you a cross section of the trough. So if you look from this side, this is what you're seeing. And this, if you add it together, you'll see 0,4 plus 0,4 plus 0,4 makes up that 1,2 meters. So if you take this flat again, that was the breadth of the sheet. And then obviously over here, you've got the 20 meters, which is the length of that particular sheet. So they've given you this nice little diagram to work with. Now, the first thing they ask here is they ask, show that the volume V is given by V equal to 1,6 sine 2 theta plus 3,2 cos theta, and that's worth 8 marks. Now, this is the part where most people look at it and they just give up. They go like, what? And if you give up over here, please, 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 people, do not give up on the next question. Because I always say to people, the reason they gave you that particular formula is because if you could not find the volume of this particular water trough in that format, you can at least use what they've given you in the next question. So even though you can't get that, you can use that in order to optimize. In other words, you can find the derivative, you can set it equal to 0, and you can solve the equation in order to get that maximum volume. So we are going to look at this problem because this is probably the most complicated part of this question, and we are going to look at this one, which is the differentiation part. Okay, so first this part. They want you to get the volume. Now in order to get the volume, you need to understand that volume is normally equal to the area of that base shape over here. So if I just color this in for you guys to see, that shape over here, given in this cross section, if I multiply the area of that with the length, which is 20, then I get the volume. So that's what you need to understand. So before I can get that volume, I need to get the area of this shape right there. So let's start with that part. Now to get the area of that shape, you need to recognize that this shape consists of a rectangle plus two specific triangles. So it's the rectangle plus the two triangles. Now the memo, if you go and look at the memo, broke it up separately. It worked out this particular triangle, it worked out the area of that one, and then it just doubled it up because they saw that those two were congruent. There's a very clever way where instead of working out this one first and then doubling it up, you can actually put these two together. So you can actually do this. Where you say, there's theta, there's 0,4, there's 0,4, and then you've got that same length over there, which this could be GB, if you realize that could be GBE, but this could also be FCD. So I can put the little D there because this could have been the FCD. So I just took these two triangles and I put them together. And this actually makes it a lot easier to do. Because if I want to work out the area of that triangle, you should spot I've got an angle that is included in these two sides. And two sides and an included angle normally means we have to use the area rule, the sine area rule. So I can work out the area of this little shape saying that is equal to a half side times the sine of the included angle. So that's 0,4 times 0,4 times the sine of the included angle, which is the sine of 2 theta. So I'm going to just quickly work that out. 1/2 times 0.4 squared is equal to 0.08. So this is 0.08 sine 2 theta. So I've now worked out the area of those two triangles over here. Now I still need to work out the area of that rectangle. So in order to work out the area of that rectangle, we realize we've got the length. Whoops, we do not have the breadth. But I can work out the breadth over here by saying I've got theta and I've got 0.5. I want this. This is my adjacent. This is my hypotenuse. So if you think about it, the cosine of theta is going to be adjacent over hypotenuse. So I can say that cos of theta is equal to, and like I said, my adjacent, which is GB, over my hypotenuse, which is 0.4, which then means that GB is equal to 0.4 cos of theta. Good. And that means the area of that lovely little rectangle is then equal to length times breadth, which is 0.4 times the 0.4 cos theta. So if you work that out, 0.4 times 0.4 is then equal to 0.16. So it's 0.16 cos theta. So overall, this trapezium, I now go and I say, if I add this area, the area of the two triangles, to this particular area, which is the area of the rectangle, that gives me the area of the trapezium. So total area is then equal to that 0.08 sine 2 theta plus this 0.16 cos theta. Now, I'm not trying to get the area, I'm trying to get the volume. So this is the part where you have to realize the volume of this shape is the area of this times 20. So I go back to this and I say my volume is then equal to 20 times 0.08 sine 2 theta plus 0.16 cos theta. And then if I distribute that 20 and I go 20 times 0.08, I end up with 1.6. So I've got 1.6 sine 2 theta plus, and now 20 times 0.16 then gives me 3.2 cos theta. And that is what the volume is of that shape. And if you compare that to what they asked, volume is 1.6 sine 2 theta there, plus 3.2 cos theta there. So I've answered those 8 marks. So yes, lots of work, but at least that part is done. Now this is actually the easy part. The easy part is now where you have to go and say, now that you know what you're trying to maximize, in this case the volume, please determine the size of theta for which the trough will have this maximum volume. So in order to do that, we're just going to use this volume, which they've given me or that I've deduced, 1.6 sine 2 theta plus 3.2 cos theta, and I'm going to say find the derivative. So when I find the derivative of this one, please remember this is going to be a chain rule because of that 2 theta inside the sine function. So I'm going to say it's 1.6. Now the derivative of sine is cos 2 theta. But please remember, because of the chain rule, I have to multiply that by 2. Plus, and then I'm going to write down the 3.2. Now, the derivative of cos theta, and this is on your formula sheet, just like the derivative of sine theta, is minus sine theta. And no, we don't really have to use a chain rule there because we've just got theta, and the derivative of theta is just 1. So I know I'm done. Okay, so now I can simplify this, and I can say this is then 3.2, because 1.6 times 2 is 3.2 cos 2 theta, plus, oops, sorry, that should be a minus 3.2 sine theta. And in order to maximize, I need to set that equal to 0. Now, you might look at that and go, oh my goodness gracious, I have no idea. People, that is a double angle right there. And because this is a double angle, I'm going to have to expand that double angle. And what do I expand it to? I expand it to sine, because this is sine. So I'll put a bracket around it and say it's 3, 2 times 1 minus 2 sine squared theta, which is the double angle identity for cos 2 theta, minus 3, 2 sine theta. Then I'm also going to go, and I don't know if you noticed, but I don't want to have these 3, 2's there. But because they're common to both of the terms, I'm going to divide it away. Make this a little bit easier to do. So I get 0 is equal to 1 minus 2 sine squared theta minus sine theta. And then I'm just going to put it in standard form, which is 2 sine squared theta plus sine theta minus 1, which then gives me a quadratic trinomial that I can factorize. So I factorize the quadratic trinomial. I get 2 sine theta times sine theta, and I go 1 times 1, and then this has got to be plus, and this has got to be minus in order to get that plus sine theta. So that means sine of theta is a half, or sine of theta is negative 1. Now, please remember, you are now trying to find theta, because that's what the question asked. The question asked over here, hence or otherwise determine the size of theta, which will give the trough a maximum value, a maximum volume. So, the first thing you need to understand is theta has got to be, in this case, an angle between 0 and 90 degrees. It doesn't make sense for this theta to become greater than 90 degrees, because then instead of having this shape, you're going to have a situation where it goes down like that and the water's not going to stay in the trough. So I know for a fact it's got to be between 0 and 90. But because this is AP Maths, we don't work with degrees, we work with radians. So I know my answer for theta has got to be somewhere between 0 and 90 degrees, which in this case is pi over 2 radians. That's just something I have to keep in mind. And that is why this particular answer is not applicable. That one is not going to work, because the only way it can be negative is if it doesn't fall into that particular range of values. Because remember, this range of values is first quadrant, and sine theta is not negative in the first quadrant, so I ignore this. So I go to this one, and when I go to this one, I make sure my calculator is set to radians, which you can see there it is, and I go shift inverse sine of a half. And I end up with 1 over 6 pi, or just pi over 6. And that's the answer. So if theta is equal to pi over 6, then the volume of this particular trough will be at a maximum. So, yeah, I know this was quite a tough question that they asked. We're going to do one more problem. The other problem is not going to be as tough as this one. I did do the first one first, just because I know this one does require quite a lot of concentration. Right, so let's move on to the other problem. Now the next problem you will see over here is also in the Advanced Program Mathematics paper 1, and it's specifically here from the 2016 paper. And what they do over here in this question 11 is they say, refer to the diagram below. A point P, now P is a variable point, so it moves on this curve, but obviously as it moves on the curve, the x-coordinate and the y-coordinate can change. So it moves along the curve defined by y is equal to 1 over x squared plus 4. So that's the equation of that particular curve. And they tell me x is greater than 0, so obviously this point can't move in there. It can only move into a positive x-coordinate. Point A lies on the x-axis, so they tell me A over here lies on the x-axis. So please remember that means point A is going to have the same x-coordinate as point P, but the y-coordinate is going to be 0. Okay. And point B is on the y-axis, so point B, if you think about it, is going to have the same y-coordinate as that point P, but it's going to have an x-coordinate of 0 because it lies on the y-axis. So this is going to be the point 0, y. And they say this thing forms a rectangle, OAPB. That's the rectangle right there. And they ask, find by using calculus methods the maximum area of this particular rectangle. So first things first, going back to the whole principle, we have to start by saying to ourselves, what am I trying to maximize? I'm trying to find the maximum area of the rectangle. So I need to write down the area of the rectangle, which is equal to length times breadth. Now in the context of this diagram, I have to then notice, but the length over here is y. And the breadth over there is x. So in this case, the area is going to be equal to x times y, y times x. And now comes the problem. The problem with this is the following. I can't have two variables. I need one independent variable, not two. And it's funny how often a lot of people don't spot the following, but this y value right there is defined over here. That is my y value. And they go like, well, how do you know this is the y value? Because P is located on that graph, and if P is located on that graph, it means it's got to satisfy, this value has got to satisfy that equation. So that means this is the relationship between x and y. So I can substitute y with this. Which then means my area is then equal to x over x squared plus 4. And this then is the area formula, or the function that I need to differentiate and set equal to 0 in order to find the maximum area. So we'll continue from there, saying my area is equal to x over x squared plus 4. I will find the derivative, because that's how I optimize, by finding the derivative. And because I'm saying it's the top divided by the bottom, I'm going to use the quotient rule. You could have moved that up and made it to the power of -1, and then you could have used the product rule, but I'm just going to use the quotient rule. So according to the quotient rule, it's the derivative of that top function x, which is 1, times the bottom function x squared plus 4, minus the derivative of that bottom function, so the function in the denominator, which is 2x, times the top function, which is x. And then I have to divide that entire thing over x squared plus 4 squared. So this is my derivative. But remember, in order to optimize, I must set my derivative equal to 0. And I'm just going to simplify this, which is x squared plus 4 minus 2x squared. Now we have discussed this before in class, where I say, if I solve a fraction equal to 0, I can actually throw this away. And the reason I can throw this away is because this will not result in a 0 answer. If a fraction is equal to 0, it's only the numerator equal to 0 that will give me that result of 0. So I can then just go straight and say x squared minus 2x squared is minus x squared plus 4. That must be equal to 0. So x squared is equal to 4, which means x is equal to, now remember, this should be plus or minus. So I'm going to write the plus or minus 2 down. But if you recall from the diagram, they specifically said x must be greater than 0. So because x must be greater than 0, I'm not going to use the negative result. I'm just going to go and say, therefore, x is equal to 2. So if x is equal to 2, the area of that rectangle will be at a maximum. But remember, read the question. If you read the question, it says, determine the maximum area. So they don't just want the x value, they actually want the maximum area. And this is the part where we now need to go and sub back. So I need to go back and I need to say, okay, so the area is equal to x over x squared plus 4. And for x equal to 2, I get a maximum area. So I need to sub x in there. So that means 2 over 2 squared plus 4, which is going to be 2 over 4 plus 4, which is 8, which is a quarter. And that quarter that is my maximum area. So just be careful, because you might have just stopped here when you said, oh, x is equal to 2. That gives you the value of x for which I have a maximum area, but it doesn't actually give you the maximum area. And that's that part that I discussed in the previous video lesson, where I said you might have to substitute this answer back into the original formula or function in order to get that maximum. So now I know the maximum area of that particular rectangle is a quarter. Right, so those were the two past paper problems we're going to do on this particular area of maximum and minimum word sums. Thank you very much.